Today we're going to give an introduction to the kinetic theory of gases. So here we have a particle which has an elastic collision with the wall, and momentum would be the mass times that velocity. So the change in momentum would be mass times the change in velocity, and minus going in the opposite direction would result in the change in momentum equals 2 times the mass times the velocity in x. However, this is just one case for one particle with a single velocity. When we're talking about multiple particles, they all have different velocities. So we talk about a distribution of velocities. So the equation starts with a constant. It's what normalizes the function. And then we have E elevated to negative energy over a constant times temperature. So this is what we call the Boltzman factor. It's always going to be an energy over a constant times temperature. This is what we call thermal energy. What we refer to as energy would simply be the kinetic energy. These are particles in motion, so they're affected by movement and by the temperature. So we have 1/2 the mass times velocity elevated to the 2, kinetic energy. Substituting the kinetic energy for the E in the equation, we are left with B, the constant of normalization, times E elevated to the negative mass times the velocity in x elevated to the 2, divided by 2 times the constant k times the temperature. Integrating this function would give us the sum of all the probable velocities of x amount of particles. So naturally, this would be equal to 1. The simplest way to understand this is if you throw a coin in the air, what is the probability of getting head? Well, that's half. And what is the probability of getting tails? Well, that's another half. And if we add both probabilities, we get 1. So the sum of the probabilities of x amount of velocities is 1. So this is useful because now we can find what is the constant b. Before beginning the integration, there's one integral that we must remember, that the integration of e elevated to negative constant a x to the 2 is equal to the square root of pi divided by a. So here we can easily identify what is a. So a would be m divided by 2k times t. After substituting, we are left with b multiplied by the square root of pi divided by mass divided by 2k times t. And this will simply be equal to 1, but leaving the constant by itself, the result would be the square root of mass divided by 2 times the constant k times temperature times pi. Now we proceed to substituting the constant b into the function. So here we're just substituting b. So the constant b would change exponentially depending on the dimension we're in. So if we're in the first dimension, it would be the square root, and velocity would be in one dimension. If we were in the second dimension, it would be 2 over 2, which is 1. So it would just be m divided by 2k t times pi in the second dimension. And in velocity, we will have two components. So it would be velocity in x and velocity in y, for example. If we are in a third dimension, then the exponent for the constant b would be 3/2. And for velocity, we would have three components. So we would have velocity in x to the 2, velocity in y to the 2, and velocity in z to the 2. So it changes depending on which dimension we're talking about. And that's all, guys. Thanks for watching. Good luck.